kinetic energy for one particle, kinetic energy for system of particles. A body is made up of several particles, so each particle has to be considered. Now, suppose we have a particle whose kinetic energy is half mv square. Let's call kinetic energy as k and differentiate both sides with respect to t. M is constant, half is constant. Derivative of v square is 2v dv by dt. Now, dv by dt, is the magnitude of tangential acceleration. It is the magnitude of acceleration which is along the motion. In case of circular motion, the tangential is along the motion. So m dv by dt is something like mass into tangential acceleration. So mass into tangential acceleration should be the tangential force. Magnitude, of course. I'm not using any vectors. So dk by dt is ft into v. Let us say that vector f and vector v are making some angle. Now when I say vector f, this is the net force I'm talking about. Net force. There may be individual forces f1, f2, f3 and so on, but this f is the net force. So ft is the component of f along the motion. So if this angle is theta, then ft will be f cos theta. We can use dot product also. Dot product also gives you the same result, fv cos theta. Here in place of ft, what would you write? F cos theta. So f cos theta into v, and f dot v is also fv cos theta. So actually they are the same. So dk by dt is f dot v. V is the velocity, and velocity is dr by dt. So f dot dr by dt. Now look at these two. Left side dk by dt, right side f dot dr by dt. These give us dk equal to f dot dr. This is the background of one of the most important things in this topic, which we will call as work energy theorem little later. So dk is equal to f dot dr. Up to this point, if you have any question, then let me know, or we proceed with the definition of work. Okay, no questions. So let's now define work. we got this relationship dk equal to f dot dr. Right side is the dot product, so it's not a vector. Kinetic energy is not a vector. How we define kinetic energy? Half mv square. It's not a vector. Yes, one can write kinetic energy as half m vector v dot vector v, but that's a dot product. The unit of kinetic energy, by the way, can be easily found kilogram for mass and accordingly for speed in standard system. And what you get is called joules in short. So joules is same as whatever you get here by putting the SI units of mass and speed. Now, left side is not a vector, right side is a dot product of vectors, so it's not a vector. We are now going to define work. F dot dr, that's called work. F dot dr is called work. Actually, we are talking about little displacement, so it's the little work. And if you want to get the total work, you would need to integrate. So this would look more appropriate. Work is integral f dot dr. Integral f dot dr is work. So if between vector f and displacement angle is theta, then it would be f dr cos theta. Integral f dr cos theta. If the angle between vector f and displacement is theta, then this would be f dr cos theta. Now, note that here f is the net force. The moment we wrote m dv by dt equal to some component of f, Newton's second law we applied. Mass times acceleration equal to force, when we say we have applied the second law. And one force alone is not supposed to be providing acceleration necessarily. Newton's second law should be applied for net force. So F here is the net force. So when we discuss the definition of work, we did say that let this be called dw, and therefore w will be integral of this. But when we discuss this w, then work is also defined for some individual force. Work is also defined for some individual force. So when we define dw like this or w like this, then here F can be the net force also, but it can be the individual forces also. So your body may be acted upon by number of forces. You can talk individually. What is the work done by gravity? What is the work done by friction? What is the work done by normal reaction? You can talk in individual way like this. You can also say what is the work done by the net force. But while work is defined for individual forces also, there is something which works for net force only, which is this relationship. Because this was derived by making use of Newton's second law, and Newton's second law talks about net force. So this will work only for net force. So to emphasize that point, we can perhaps add that subscript fnet.dr and when we say W equal to fnet.dr, well, we have found the total work done by all forces acting on some particle, right? And if you just compare these two, K2 minus K1 is also this, and work done by all forces, net of all forces. Compare these two. And you get the very important work energy theorem. Work energy theorem, right? Work energy theorem does not talk about potential energy. We have not even defined potential energy yet. So in work energy theorem, W is the work done by the resultant of all forces, while work can be done by individual forces also. But in W equal to K2 minus K1, it is all forces. You can't apply work energy theorem for isolated forces. That's wrong. For isolated forces, you can talk about isolated work done by one force, work done by another force, work done by third force, like that. That's way you can talk. Now, when we talk about work done by resultant force, then F net is F1 plus F2 plus F3 and so on. So that's the work done by the net force. This is the work done by the net force. But you will find that work done by the net force is equal to the sum of the work done by individual forces. That's the result we are going to get very soon. Integral F1 dot dr, integral F2 dot dr, integral F3 dot dr, and so on. W1, W2, W3 and so on. So whether you calculate individual work or you calculate the overall work by the overall force, the result is going to be the same. Work is a scalar, so that's expected. Work is a scalar. How did we define work? Dot product of something. So work is scalar. So you can add work like numbers. Now, this work is not effort of English. You do a lot of effort and you can sweat also, but this work has nothing to do with sweating. Yes, you may get tired when you sweat. So you can say I'm losing energy, But that energy is not mechanical energy. That energy is your internal energy, the food that you eat. It is due to that. Yes, go ahead. K2 is the final kinetic energy and K1 is the initial kinetic energy. K2 is final kinetic energy, K1 is the initial kinetic energy. Now I was talking about you are doing a lot of effort, but displacement is not taking place. There may be other forces also acting, but even then no displacement is taking place. You try to push a train, put as much effort as you wish, train won't move. So if the train does not move, displacement is not there, dr vector 0. So the work done by you is 0 in that case. So work and effort are different things. Work of English is not as the work of physics. Now, one more important thing to understand is that work can be defined for different forces. For displacement to take place, some force does not have to be the cause of displacement. Some force does not have to be the cause of displacement. In the definition of work done by a specific force. Okay, let me not complicate. Work done by a specific force is given by Fd cos theta. I have removed that integral, etc. If force is constant, then you can go for the simplified thing. Now here, displacement does not have to be due to F. Maybe some F2 is there and due to that displacement is taking place, or it is actually due to all. If 10 forces are acting on a body, then displacement takes place because of the resultant of those 10. What I am trying to say is, work done by a specific force has some D in it, and that D does not have to be only due to F. That D is due to the resultant of all of the forces. So F does not have to be the cause of D. For example, you pull some book on the table, at the table. You pull some book kept at the table, right? A book is going to the right side. Can gravity take credit for it? No. Gravity is acting downwards. Gravity can never take credit for a motion which is perpendicular to it. So did gravity move it? No. What is the work done by gravity in this process when you move the book on a kept at some table? What is the work done by the gravity? To answer that, you would use the same formula, and D will be that D, but theta would be 90. Theta would be 90, but D will be that D. If the book has traveled by 1 meter, then D will be 1 meter, even though gravity did not move it by 1 meter. So that's very important to understand, that the force does not have to be responsible for the displacement in all cases. And one more point is that force must be in contact when the motion is taking place. Force must be in contact when the motion is taking place. So just giving some sudden jerk, that's not what the meaning of this thing is. What is the meaning of FD? The meaning of FD is that when the complete D has taken place, every single point of when D was taking place, at every single point of the motion, F was acting. That's the meaning of FD cos theta. It can't happen that you hit some ball and then ball is gone. After the ball is hit, it is experiencing no force from the object which was used to hit the ball. The tennis racket hitting tennis ball, hits the ball, tennis racket hits the ball, ball is out of the contact. It is not even in contact with the racket when it is in air. So racket is not applying force when the ball is in air. So when the ball is traveling d distance in air, you would not say force applied by the racket is F. Force applied by the racket is 0, 0, 0, 0, 0, 0. Whenever the ball is in air, force applied by the racket is 0. Only for a very small period of time, ball is in contact with the racket, and that's it. So a very important point is that to apply this type of equation, D should be such that F is in contact with the body throughout that D. So in case of tennis example, once the ball leaves the tennis racket is not going to do any work. Force is 0. Yes, there may be air friction, etc. Air friction will be there whenever ball is in air. Air friction is going to be there. Throughout that whole D, air friction is going to be there. Right? But that's a different force. So, in contact is something which is very important. In contact. Force should be in contact throughout D. Yes, any questions? Let me know. At this point, don't bother about system. Treat this as particle. Treat this thing as particle. So all you need to do is final minus initial. That will be the increase. $375 joules is the answer you should get. And if you would like this to be discussed on the board, then raise your hand. "12 kmph means how many meter per second? Ten by 3. And 6 kmph means 5 by 3. M by 2 is common. (90 by 2 is 45. Just put the values. You will get the answer in joules. Let me know if you have any questions or we move on. Next. Yes, 625 joules. If you would like this to be discussed on the board, then raise your hand. Well, work has no direction, so the answer should be minus 400 joules. When you have force and displacement in opposite directions, then theta, when vectors are anti-parallel, theta is 180 degree. And that will get you the minus sign. Any questions? Let me know. Let me cover up a little bit more theory related to constant force, this type of result. For some specific force, work done is this. Now, if force is constant, its direction is also constant, its magnitude is also constant. In other words, vector f is constant. Then, after this step, we can take f out of the integral. Right? Now regarding that fd cos theta result, there are many situations where not only f but also theta, both are constant. You are pulling some suitcase at fixed angle. Suitcase is moving in this direction. Then theta is fixed. So in that case, even cos theta comes out and you get f cos theta integral dr. If suitcase goes by d distance, integral dr is simply d. So fd cos theta. S is constant, theta is constant. Sometimes theta can change even though vector f is constant. Can you imagine this situation? Theta is changing but vector f is constant. Dr vector is changing. So even though vector f is fixed, dr vector may change and that may change theta. Say for example, this is the table, book is at some height. Book can be brought straight down or book can be brought by some curved path. Now as far as force is concerned, Earth is going to apply mg force. Let's talk about work done by Earth in this case. So Earth is going to apply mg force, whether you bring the book straight down or curved down. And F vector is fixed. But then look at displacement. Several drs you will find are directed in different angles. So dr vector is not fixed. Theta is not fixed. So for a case like that, this is what one has to use. But in many cases, theta is fixed, and I think this was one such case. Yes, theta was fixed, 180. Right? So if theta is fixed, F is fixed, you can straight away use FD cos theta. Now, how does one handle this type of situation in the context of Earth? Gravity, that is. Work done by gravity we are talking about now. You can also say mg. As far as straight fall is concerned, things are really easy. This is a table. Let's say book is at height h, a particle is at height h. In this vertical case, theta is same, force is same. Force is down, displacement is down, theta is 0, answer is mgh. Now how about some complicated curve? Visualize the curve as staircase. In this particular drawing, one can say, well, it is not looking like a curve. This staircase is not looking like a curve. Yes, it is not. But if you have a polygon, triangle and circle, very different. Quadrilateral and circle, very different. Pentagon and circle, very different. But if you make hexagon, heptagon, octagon, if you keep on increasing the sides of polygon, then you find that it comes closer and closer to the circle. Circle is nothing but a limiting case of a polygon where sides of polygon approach infinity. So imagine number of these fellows approach infinity. Then it would be a justification. But to show it, I have to show some length. Now, for this path, mg is down displacement is to the right. Work done will be 0. From here to here, same story. Displacement to the right, force mg down. 0 work. 0, 0, 0, 0, 0, 0. And these fellows add mg this h1, mg this h2, mg h3, mg h4, mg h5, mg h6. If you add all these h's, h1, h2, h3, you will get h. And if you like to increase complication, no trouble. Up and down if you do, then some h's will be negative, some h's will be positive. I mean, some work will be negative, some work will be positive. Eventually you are going to get the same this h. Whether the path is straight down, curved, this curve down, this curve, doesn't matter. A very interesting result actually. The path doesn't seem to matter. Whether you drop the book, you take it in this trajectory, you take the book in this trajectory. As far as the work done by gravity is concerned, how you bring the book down does not seem to matter. The work done by gravity in all cases will be mgh. Provided the book is close to the surface of the earth, that means g does not change significantly. If you bring a book from moon to the earth, then it's a different story. That can also be handled in gravitation topic. But for mgh to work, g should be constant, and that happens when distances from the surface of the earth are no way comparable to the radius of the earth. Any questions about work done by mg? Let me know. Try this. Let me check. The answer I have is 245 joules. If you would like this to be discussed on the board, then raise your hand. If you have any question, then let me know. Okay. Okay. Constant force, constant angle. F d cos theta. Vector F is down, mg is down. Displacement vector is along AB. So the angle between the two of them will be 60. That's it. Put theta equal to 60, put other values, and see if you are getting 245 or 250. Any questions? Let me know. some particle moves from this position vector to this position vector. Consider this force acting on it throughout its journey. Now this is constant force just like gravity's case, paths should not matter. So what is the work done? What is the work done by this force? Yes, 0 is correct. If you would like this to be discussed on the board, then raise your hand. Any question if you have, then let me know. This one is interesting. Let me check. Now let me ask you one thing. You have to tell some technical name. You know different types of forces, gravitational, electromagnetic. And electromagnetic forces are of different types. If you hold something in your hands, reaction force is one electromagnetic force. But then reaction force here is perpendicular to the motion. So how can it do any work? Well, I think I would let you think further. But I will just tell you one thing, that the answer is not 0. So don't just give me the numerical answer, but also provide explanation that who could it be which is doing non-zero work. Okay, so that's your assignment. And we stop at this point.